Tonight, we're going to take a serious look at what it would actually take to travel to the nearest star, Proxima Centauri, 4.24 light-years away. It sounds like the kind of thing humanity will figure out eventually. Better rockets, better technology. Give it a few centuries. But here's what that assumption gets wrong. This isn't a problem that scales with better engineering. The journey to Proxima Centauri runs into physics, biology, and mathematics that don't bend for ambition. And when you work through the numbers honestly, the fuel required, the radiation accumulated, the decades spent inside a sealed ship with no way back, what comes out the other side is something most people are completely unprepared for. By the end of tonight, you're going to understand exactly what this journey demands, why it is unlike anything humanity has ever attempted, and why some version of it will almost certainly happen anyway. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Proxima Centauri is the closest star to our Sun. That sentence is technically accurate and almost completely misleading at the same time. Because when most people hear closest star, they imagine something like driving to the next town. A long trip, sure. But fundamentally, the same kind of thing as any other trip. It isn't. Proxima Centauri sits 4.24 light-years from Earth. A light-year is the distance light travels in 1 year, moving at 186,000 miles per second. That's not a unit of time. It's a unit of distance that uses the speed of light as its ruler, because the distances involved are so large that any other ruler becomes absurd. At that speed, light covers about 5,870 billion miles in a single year. Multiply that by 4.24 and you get the distance to Proxima Centauri. About 25 trillion miles of empty space, radiation, cold, and silence between us and the nearest other star. Proxima Centauri is a red dwarf. It belongs to the most common class of star in the galaxy, which is somewhat humbling, given that most people couldn't name a red dwarf by sight. It has about 12% of the Sun's mass, about 14% of the Sun's diameter. It emits only about 0.17% as much light as the Sun, so dim that despite being the closest star to Earth, you cannot see it without a telescope. Its apparent magnitude from Earth is about 11, well below the 6 or so that the naked human eye can detect under ideal dark sky conditions. If you replaced our Sun with Proxima Centauri, Earth would be plunged into something close to total darkness. The sky would look like a moonless night that never ended. Plants would fail within weeks. Temperatures would plunge. Proxima is a faint, small, cool star that happens to be nearby. It's part of a triple star system, usually called Alpha Centauri. The other two members, Alpha Centauri A and Alpha Centauri B, are the ones you can actually see from the southern hemisphere as the bright, third brightest star in the night sky. They appear to the naked eye as a single point of light, but a small telescope resolves them into two distinct suns. Alpha Centauri A is slightly larger and more luminous than our Sun, about 1.1 solar masses and roughly 1.5 times the Sun's luminosity. Alpha Centauri B is slightly smaller and cooler, about 0.9 solar masses and about half the Sun's luminosity. They orbit each other over a period of about 80 years, in an ellipse that brings them as close as 11 astronomical units and takes them as far as 36 astronomical units apart. That orbital dance takes them through separations ranging from roughly the distance between our Sun and Saturn to well beyond Neptune's orbit. Proxima Centauri orbits both of them at an enormous distance, perhaps 15,000 astronomical units. So far out that some astronomers have questioned whether it's genuinely gravitationally bound to the pair or just passing through the same neighborhood on a coincidental trajectory. Recent measurements of proper motion and radial velocity suggest Proxima is indeed part of the system. But Proxima is at such a vast remove from its two companions that for any practical purpose of interstellar travel, we're talking about reaching three separate stellar objects. And Proxima, being the closest, is the one that gets the attention. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri. They named it Proxima Centauri b. It was found through the radial velocity method, which detects the tiny wobble a planet induces in its star's motion as they orbit their common center of mass. The planet has a minimum mass of about 1.27 times that of Earth. It orbits at a distance of about 0.0486 astronomical units from its star. It completes one orbit every 11.2 days. A year on Proxima Centauri b is 11 days long. Its orbit is closer to its star than Mercury is to our Sun. But because Proxima is so much dimmer and cooler than the Sun, that close distance places Proxima Centauri b in the habitable zone, the region where liquid water might theoretically exist on the surface under the right conditions. In 2019, astronomers announced possible detection of Proxima Centauri c, a second planet orbiting farther out with a period of about 5.2 years. Colder, likely not habitable. In 2020, evidence for Proxima Centauri d was reported, a smaller body orbiting even closer to the star, with a period of just 5 days. So there may be a small system here. 3 planets around one red dwarf, with one of them Proxima b in the habitable zone, the closest known planetary system to ours, and we cannot reach it with anything we currently possess. The Parker Solar Probe is the fastest spacecraft humanity has ever built, 430,000 miles per hour during its closest solar approaches. At that speed, the trip to Proxima Centauri would take about 6,700 years. Voyager 1 has been traveling since 1977 and is now in genuine interstellar space, moving at about 38,000 miles per hour relative to the Sun. Pointed at Proxima, it would arrive in roughly 75,000 years. These numbers aren't failures of engineering. They're physics, doing exactly what physics does. Space is genuinely this vast, and the gap between vast and reachable is where every serious plan to visit another star has to begin. A crewed mission to Proxima Centauri needs one thing above everything else: speed. Genuinely useful speed, not the kind we've managed so far. Not Parker Solar Probe speed. Not Voyager speed. Something in the neighborhood of 10% the speed of light, or perhaps higher if you want to arrive before multiple generations have lived and ended aboard the vessel. 10% of the speed of light is about 67 million miles per hour. At that speed, the journey to Proxima Centauri takes about 42 years. One way. That's the best-case baseline for a crewed mission using propulsion technology considered plausible, not current, not guaranteed, but at least grounded in physics that doesn't require overturning everything we know. 42 years. If you boarded the ship at 30 years old, you'd arrive at 72. You'd spend your entire adult life inside the vessel. Every birthday, every year of your 30s, 40s, 50s, 60s. Gone. In a metal hull, traveling through nothing, toward a destination you can only see as a dim red point of light that grows imperceptibly brighter decade by decade. And that's before we even discuss propulsion, how you actually reach 10% light speed in the first place. The honest answer is that no propulsion system we've built can get a crewed ship to 10% light speed. Not even close. Chemical rockets, the kind that have carried every human being into space since Yuri Gagarin's flight in 1961, are spectacular machines by the standards of our planet. They're completely inadequate for interstellar travel. The exhaust velocity of the best chemical propellants tops out around 2 miles per second. 10% of the speed of light is about 18,600 miles per second. The ratio between where we are and where we need to be is roughly 10,000 to 1 on exhaust velocity alone. The Tsiolkovsky rocket equation makes this concrete. It describes the relationship between exhaust velocity, the ratio of fuel mass to payload mass, and the final velocity you can achieve. The equation is merciless in what it demands. To reach 10% of light speed with a chemical rocket, you'd need a fuel-to-payload mass ratio so extreme that no physical structure could possibly contain it. The numbers become physically absurd before they become sufficient. This is not an engineering problem that better materials can solve. It's a thermodynamic constraint built into the maximum energy available from chemical bonds. Nuclear propulsion changes the calculation. A nuclear thermal rocket heats propellant using a fission reactor and expels it at exhaust velocities several times higher than chemical engines can manage. Project Nerva, tested by NASA between the 1960s and early 1970s, proved the concept works. These engines could realistically cut interplanetary travel times significantly. But even nuclear thermal propulsion doesn't get a ship to interstellar speeds. You'd achieve velocities useful within the solar system. For crossing to another star, you'd still need thousands of years. The next step up in energy density is nuclear pulse propulsion. This was seriously studied beginning in the late 1950s under Project Orion. The concept is exactly as audacious as it sounds. You detonate nuclear bombs behind a massive steel pusher plate connected to the ship by enormous shock-absorbing struts. Each explosion accelerates the ship forward. You repeat this at intervals. The cumulative effect over hundreds or thousands of detonations builds to speeds that no continuous burn engine could achieve. The physics works. Detailed analyses suggested an Orion-class interstellar ship could reach 3 to 5% of the speed of light. At 5%, Proxima Centauri is about 85 years away, still longer than most human lifetimes. But it puts the destination within range of a multi-generational crew or a single long-lived crew if medicine advances sufficiently. The problems with Project Orion were not primarily technical. They were political and legal. An Orion-type spacecraft launching from near Earth would shower the surface with radioactive fallout from hundreds or thousands of nuclear detonations during the acceleration phase. The Partial Test Ban Treaty of 1963, prohibiting nuclear weapons tests in the atmosphere and in space, effectively ended the concept's prospects. Building the infrastructure to assemble such a ship in orbit, away from Earth's biosphere, would require a space industrial capacity that doesn't exist. Still, the physics of pulse propulsion hasn't been invalidated. It sits in the category of concepts that work in principle and were halted by circumstance rather than fundamental impossibility. Fusion propulsion is the next rung. Instead of fission, A fusion rocket fuses light atomic nuclei, deuterium, helium-3, or other hydrogen isotopes, releasing energy at conversion efficiencies that dwarf fission. The exhaust velocities achievable with a fusion drive are dramatically higher than any fission approach. Project Daedalus, a design study conducted by the British Interplanetary Society through the 1970s, worked out what a fusion-propelled interstellar probe might look like in detail. The design called for a two-stage unmanned probe intended to reach Barnard's star, about 6 light-years away, in roughly 50 years. The final velocity was about 12% of the speed of light. The ship would weigh about 54,000 tons at launch. About 50,000 tons of that would be propellant, primarily deuterium and helium-3. The payload, the actual scientific instruments, would be about 500 tons, less than 1% of total launch mass. This illustrates the fundamental reality of rocketry. To accelerate meaningful mass to interstellar speeds, you need enormous amounts of propellant. Even with fusion, the mass ratio demanded is punishing. The Project Daedalus team concluded their design was physically feasible. Nothing in the engineering violated known laws. But it required mastering controlled fusion for propulsion, which we haven't achieved even for stationary power plants after decades of research, and developing industrial capacity to manufacture and handle tens of thousands of tons of specialized fuel, including helium-3, which barely exists on Earth. You'd have to mine it from the Moon or from Jupiter's atmosphere. Neither capability exists. Antimatter propulsion is the theoretical upper bound on energy density from known physics. When matter and antimatter particles meet, they annihilate completely. 100% of their combined mass converts to energy, according to Einstein's equation. An antimatter drive could theoretically accelerate a spacecraft to a substantial fraction of light speed. The problems are severe and not minor engineering details. Antimatter doesn't occur naturally in useful quantities. Every particle of antimatter has to be manufactured in particle accelerators, one particle at a time. Current global production capacity for antimatter is in the range of nanograms per year. A crewed interstellar mission would require grams or kilograms. The gap is 9 orders of magnitude. Storing antimatter requires containment so perfect that any failure ends the mission immediately and catastrophically. If antimatter touches ordinary matter, which is everything on a spacecraft, it annihilates instantly. Antimatter propulsion is not impossible in principle. It's just so far from current capability that it belongs in a different era's engineering agenda. The most widely discussed near-term concept for sending something to Proxima Centauri is breakthrough starshot. The project proposes using ground-based laser arrays to accelerate extremely lightweight probe chips, a few grams each, equipped with reflective light sails to about 20% of the speed of light. The probes would coast to Proxima in about 20 years and make a brief flyby, transmitting data back to Earth. It's a credible concept for an unmanned flyby probe. For a crewed ship, it's not applicable. You can't put people in something the size of a postage stamp. Scaling up a laser sail approach to carry meaningful human habitat mass runs into fundamental thermal and structural limits on what sails can withstand under intense laser irradiation. And the energy required grows with mass in ways that quickly become impractical. The honest answer, sitting where we are today, is that we have no propulsion system ready or anywhere near ready for a crewed voyage to Proxima Centauri. We have concepts. We have physics that doesn't forbid it. We have design studies. But the gap between today and a functional interstellar drive is measured not in years, but in generations of technological development. Suppose you take the longest possible view, and suppose humanity spends the next several centuries building toward this. Fusion power becomes practical. Space-based industry becomes routine. Mining operations extend across the solar system. We have experience maintaining closed ecosystems for decades at a time in large orbital habitats. And eventually, we build a ship. A real ship. Something capable of carrying people, supplies, equipment, and enough fuel to accelerate to interstellar velocity and, critically, slow down again when it arrives. This second part is something that often gets lost in discussions of interstellar travel. You have to stop. If you arrive at 10% of the speed of light and don't decelerate, you fly through the Proxima Centauri system in hours. Everything you came to study, every observation you crossed 42 years to make, passes in a few hours as you barrel through at 67 million miles per hour and vanish into the interstellar void beyond, with no way to reverse course. All that effort, all those years. For a brief glimpse, you could barely process before it's gone. Deceleration requires essentially as much energy as acceleration. Whatever propellant the ship burned, getting up to speed, it needs to burn roughly the same amount slowing down. This doubles the fuel requirement before you've even started working on life support, shielding, or the crew section. The rocket equation compounds this mercilessly. More fuel at launch means more mass. To accelerate means even more fuel to move that mass. There are alternatives to carried deceleration propellant. A magnetic sail deploying on approach to the target star would interact with Proxima's stellar wind-charged particles streaming outward, and the drag this creates would slow the ship. The problem is that Proxima is a red dwarf with a stellar wind that's intense near the star, but relatively weak at the distances where you'd first deploy the sail. The braking force is limited. You decelerate, but slowly, adding potentially years to the approach phase. A photon sail, using Proxima's own light for braking, is another option. Proxima's low luminosity, only 0.17% of the Sun's output, means the available radiation pressure is small. It would work in principle, but the sail required to gather enough photons would be enormous, and the deceleration time would stretch over many years. One proposed architecture separates the problem. Send an unmanned laser sail probe decades ahead of the crewed ship. The probe uses photon braking to gradually enter the Proxima system. Once there, it sets up a powerful laser transmitter. The crewed ship deploys a reflective sail facing backward, and the laser from the unmanned relay beams power at this sail to decelerate the ship. The energy for deceleration comes from the destination end, not from fuel the ship carries. Elegant in principle. Requiring the unmanned probe to arrive safely, survive in the Proxima environment, set up functional equipment, and then accurately aim a laser at an incoming ship that's years away. Every step has failure modes. For the purposes of this journey, assume the ship carries its own deceleration fuel. The mass penalty is severe. Accept it and move on. Now, the ship exists. The fuel is loaded. The crew has been selected, trained, and mentally prepared for what they're about to do. They seal the hatch. The ship begins to accelerate. Let's talk about who these people are. Not as characters in a story, as the actual kind of humans who would be chosen and would choose this. The selection criteria would be the most demanding in human history. Physical health is the entry requirement. You need people who will not develop disqualifying health conditions in the first 20 years of the journey, because there's no way to return them, and the crew is small enough that losing someone to preventable illness matters. Every major organ system would need to be in excellent condition. Cardiovascular health that can sustain a life in partial or artificial gravity for decades without deteriorating faster than the ship's medical capabilities can manage. Cancer risk profiles as low as possible, because you're about to expose these people to elevated radiation for 42 years. Genetic screening for heritable conditions that might emerge later in life. None of this is discriminatory. It's actuarial. You're trying to predict who will still be functional on the day the ship enters the Proxima system. Psychological health is even more important and much harder to screen for. Performance under stress is one thing. Sustained performance across years and decades of monotonous, confined, high-stakes living is another. Every known personality trait associated with long duration, isolation tolerance would be a positive factor. Conscientiousness, emotional stability, adaptability, the ability to find meaning in routine, the ability to maintain functional relationships with a small, fixed group of people across very long periods, low need for novelty, high capacity for self-directed structure. None of these traits guarantee success over 42 years. They just reduce the probability of failure. Technical expertise matters. The crew would need enough aggregate knowledge to manage every critical system the ship carries. But the technical knowledge is almost secondary to the psychological and interpersonal profile. You can train someone to operate life support systems. You cannot easily train someone to tolerate 20 years of the same faces in the same corridors without becoming someone who makes the mission harder for everyone else. The final and perhaps most important criterion is something harder to quantify. The genuine ability to accept that this is permanent, that Earth is behind them, that the people they love are aging and living full lives while messages crawl back and forth at 4 years per exchange, that they will not return. People who can hold that knowledge, sit with it, and still choose to go anyway. There aren't many of them. There never will be. The ones who board this ship will be, in a particular way, unlike anyone who has lived before. The acceleration phase doesn't feel dramatic from inside the ship. If the fusion engine burns at a fraction of standard gravity, which is both physiologically tolerable and fuel efficient, the sensation inside the rotating habitat ring is simply weight, similar to normal Earth gravity. Courtesy of the centrifuge, the engines might burn for months to reach interstellar velocity. During this time, the solar system slowly falls away behind. Familiar landmarks disappear. Mars passes from a disk to a point. The asteroid belt becomes indistinguishable from the background. Jupiter, the largest planet in the solar system, visible as a bright disk, even from Earth, diminishes to a bright point in the rear instruments, and then to just another light in the field. Saturn, Uranus, Neptune, each one a milestone, a marker of how far the ship has come from the world it launched from. And then the solar system's official outer boundary, the heliopause, at about 120 astronomical units. Beyond this, the sun's magnetic bubble ends. The solar wind that has been flowing outward from the sun and filling the heliosphere with charged particles thins and stops. The interstellar medium takes over. The first spacecraft to cross this boundary was Voyager 1, and the crossing was detectable in its instruments. The magnetic field environment changed character. The particle density changed. The nature of the surrounding space became different in measurable ways. The crew of an interstellar ship would see this in their instrument readings too. The sun is now a star. The brightest star in the sky from this vantage point, yes. But a star. Its appearance in the forward cameras has shrunk to the point where it's no longer the overwhelming presence it was. It's a very bright point. The crew is accelerating away from it. And there are still about 4 light-years of travel ahead. The engines cut to a lower output. Coasting velocity has been reached. The coasting phase begins. This is the long middle of the journey, the part that lasts for decades. In the coasting phase, the ship is moving at 10% of the speed of light through the interstellar medium. From outside the ship, this velocity is extraordinary. No human-made object has ever moved this fast. But from inside the ship, you can't feel it at all. There's no wind. No vibration from interaction with the medium. The interstellar medium is too sparse for that. No sensation of motion. The only things that indicate the ship is moving are the instruments and the very slow, almost imperceptible shift of nearby stars against the background of more distant ones. At 10% of light speed, the parallax of even nearby stars changes slowly enough that it takes months or years of continuous observation to notice. The stellar field looks essentially static. The apparent brightness and color of stars ahead and behind shifts slightly due to the Doppler effect. Stars ahead look marginally bluer, stars behind marginally redder, but at 10% light speed. This is subtle enough that the crew would need instruments to measure it. The experience of traveling at 67 million miles per hour is, visually, indistinguishable from sitting still in deep space. This is one of the genuinely strange psychological facts about interstellar travel at these velocities. Nothing confirms the journey is happening, except the passage of time and the data from instruments. Every day is the same. The corridor looks the same. The air tastes the same. The faces around you are the same. The schedule is the same. The instruments report steady progress, and you know intellectually that you're moving. But there is nothing experiential to anchor that knowledge to. This has effects on people. The absence of any sensory confirmation of motion, combined with the unchanging environment, tends to produce a kind of temporal confusion. Days blur into weeks. Weeks into months. The calendar marks years, but the subjective sense of time passing is warped. This is documented in isolation research and in long-duration spaceflight. The International Space Station astronauts report this effect on missions as short as 6 months. 42 years of it is genuinely uncharted territory. No study has ever followed people in confinement for this duration. No psychology researcher has a dataset that extends past a few years. Extrapolating to decades is possible in theory, but extrapolations across an order of magnitude in duration have a tendency to miss things. The psychological architecture of the crew during the coasting phase is the most important factor in whether the mission succeeds. More important than any engineering parameter, because the engineering either works or you fix it. Human psychology doesn't respond to fixes the way machinery does. The first year is the exciting one. The launch is behind them. The initial acceleration is complete. Every instrument reading from the interstellar medium is genuinely novel. The crew is collecting data that has never been collected by humans before. The sense of mission is high. Motivation is strong. By year 3, the novelty has faded. The instruments are still collecting data, but the day-to-day reality of life aboard the ship has asserted itself over the sense of mission. Relationships have settled into patterns. People know each other's habits, their moods, their private irritations. The psychological armor that people maintain in social interaction, the effort everyone makes to present their better qualities to others, starts to wear thin when those others are the only people in your world and have been for 3 years. You don't stop making the effort, but it takes more energy. Small frictions that were invisible in year 1 are daily minor events by year 5. By year 10, they're simply part of the texture of life, either managed or accepted. Studies of isolated communities consistently identify what researchers call the third quarter phenomenon. In any long-duration isolated mission, morale and cohesion tend to hold relatively well in the first quarter and last quarter. The first quarter, because the mission is still fresh. The last quarter, because the end is approaching and the sense of purpose revives. The third quarter, past the halfway point, but still far from done, is where the real psychological weight accumulates. For a 42-year mission, the third quarter begins somewhere around year 22 and ends around year 32. The crew's late 40s to early 60s. Past the midpoint, still more than a decade from arrival. No existing research has studied humans in isolation for anything close to this duration. The crew would have every resource the planners could provide. Psychologists among the crew. Structured programs to maintain social cohesion. Cultural practices, celebrations, rituals designed to give time meaning and provide a sense of continuity. Communication from Earth, delayed by years, but still a connection. These resources matter. They help, but help is not the same as prevent. There will be episodes of genuine breakdown during 42 years. They are statistically certain in any group of humans under sustained confinement. The question is whether the crew has the structures and resources to absorb those episodes without the mission spiraling into something worse. Governance is one of the harder problems. A captain appointed before launch governs by designated authority at the start. But authority over decades needs legitimacy, and legitimacy in a closed community depends on behavior, not just rank. The governance structure that makes sense for year 1 may not make sense for year 25. The crew would need to maintain functional social institutions, decision-making processes, conflict resolution mechanisms, norms about behavior and responsibility across generations of their own psychological evolution. No one has designed a governance system for this scenario because no one has needed to. History offers cautionary examples of isolated communities under stress. The Pitcairn Island mutineers, after founding their colony on a remote Pacific island in the 1780s with no outside contact, descended into conflict and killing within a few years. The causes were familiar: resource competition, relationship conflicts, status disputes, the compounding effects of stress with no release valve. A generation ship crew would have enormously better preparation. They'd have training, counseling resources, pre-established frameworks. But they'd also be isolated longer, with higher stakes, and with no option to leave. The comparison isn't fair, but it's informative. The biology of the crew during the coasting phase faces challenges that operate in parallel to the psychology. The human body in space is not the human body on Earth. It's running the same hardware in a radically different environment. Bone density loss is the most extensively documented effect of long-duration spaceflight. In weightlessness, bones receive no loading forces. The skeleton exists on Earth primarily to support the body against gravity. Remove gravity, and the body gradually reduces bone density because maintaining it costs metabolic resources that seem unnecessary. Astronauts on the International Space Station lose about 1 to 2% of bone density per month, despite rigorous exercise countermeasures. 6 months in orbit produces measurable bone thinning that requires months of rehabilitation to partially recover. The engineering solution for an interstellar ship is artificial gravity through rotation. Spin a section of the ship, and the centrifugal effect simulates gravitational pull. The occupants' bodies experience an outward force that feels like weight, and the skeleton responds by maintaining the density needed to support it. For the simulated gravity to be convincing enough that bones stay healthy, the rotating section needs to be large enough that the rotation rate required doesn't cause chronic motion sickness in the crew. The human vestibular system becomes confused by fast rotation and produces a kind of nausea that doesn't resolve quickly. The larger the radius of the rotation, the slower it needs to spin to produce any given centrifugal acceleration. A habitat ring with a radius of 50 meters, rotating at about 4 to 7 revolutions per minute, could simulate somewhere between 1/3 and 1 full standard gravity, depending on exactly how fast it spins. Some crew members would find the upper end of that range comfortable. Others might have vestibular sensitivity that requires slower rotation, which means settling for lower effective gravity. The ship would need a habitat ring that's large enough to rotate slowly enough that essentially all crew members can tolerate it. That means building something large. Structures that large are not launched from Earth's surface. They're assembled in orbit, which means we're back to needing a space industrial base that doesn't yet exist. Assume it exists. Assume the ship has a functioning habitat ring, producing sufficient artificial gravity to keep the crew's bones and muscles healthy. There are still biological effects that artificial gravity through centrifuge doesn't address in the same way that true gravity does. Fluid dynamics within the body in a rotating habitat are subtly different from a constant gravitational field. The gravity vector changes direction smoothly across the body, but not identically to a true gravity field. Whether these subtle differences produce long-term health effects over decades is genuinely unknown. We don't have data. We'd be finding out in real time on the mission. The immune system is another biological concern. In space, immune function behaves differently. Latent viruses that the immune system normally keeps suppressed can reactivate. Epstein-Barr virus has been detected, reactivating in astronauts on relatively short missions. Cytomegalovirus. Similarly, in a closed environment with a small, fixed group of people for decades, the microbial ecology of the ship evolves. The bacteria, fungi, and viruses living on and in every crew member begin to equilibrate across the group as everyone shares the same recycled air, the same water, the same surfaces. By year 5, the microbial community of the ship is already different from what it was at launch. By year 20, it has evolved in ways that reflect the specific conditions inside the ship, the radiation environment, the recycled atmosphere, the humidity levels, the particular mix of human hosts. This is genuinely novel territory. No one knows what a human microbiome looks like after 20 years in a sealed interstellar ship. It might be essentially fine. It might produce new health challenges that no physician in history has ever encountered, because the conditions that produce them have never existed before. Medical care would need to be comprehensive and adaptive. The ship's physicians would need to handle anything from appendicitis to cancer to novel infections with no established treatment history. Pharmaceutical supplies would need careful management. Some medications degrade over time. A drug effective in year 1 may have lost potency by year 30. The ship would need either refrigerated storage systems for temperature-sensitive medications or the ability to synthesize critical pharmaceuticals from precursor chemicals carried aboard, or some combination of both. The aging of the crew is a medical planning challenge in itself. If the crew departs in their 30s, they arrive in their 70s. The medical profile of a 70-year-old is not the medical profile of a 30-year-old. Heart disease rates increase significantly with age. Cancer rates increase. Vision and hearing degrade. Cognitive function changes. Joints deteriorate. For a crew of 50 people aging from their 30s to their 70s over the course of the mission, statistical expectations would include multiple cases of serious age-related conditions. Cancer, several times at minimum. Cardiovascular events. Strokes. These would be managed aboard the ship with whatever medical capability the mission carried. Some would be managed successfully. Some wouldn't. The crew knows this. The mission plans for it. It's still hard when it happens. Now, let's add the radiation. This is the factor that most fundamentally distinguishes interstellar space from any environment humans have inhabited. Inside the solar system, the sun's magnetic field and the solar wind form a protective bubble called the heliosphere. This bubble deflects a significant fraction of incoming galactic cosmic rays. Atomic nuclei accelerated to extraordinary energies by violent events in the galaxy. Inside this bubble, we're partially shielded. Not completely. Even on Earth's surface, cosmic rays make it through the atmosphere at a reduced flux. Astronauts in low Earth orbit, inside Earth's own magnetic field, receive radiation doses roughly 150 to 200 times higher than people on the ground. Beyond Earth's field, but still within the solar heliosphere, the exposure is higher still. In the interstellar medium, the heliosphere's protection is gone. The cosmic ray flux is measurably higher than inside the solar bubble. Galactic cosmic rays are atomic nuclei, mostly protons and helium nuclei, but also heavier elements, including iron, accelerated to speeds approaching light by supernovae, neutron stars, active galactic nuclei, and other high-energy events. When they hit matter, they don't stop cleanly. A single high-energy, heavy nucleus can shatter atoms along its path, producing cascades of secondary particles. In biological tissue, this cascade breaks chemical bonds and tears through DNA in ways that X-ray radiation would need far greater doses to replicate. The human body has DNA repair mechanisms that handle normal background radiation effectively. Those mechanisms are overwhelmed by prolonged high-level cosmic ray exposure. Astronauts on the International Space Station accumulate a radiation dose increase of about 1% to lifetime cancer risk per 6 months. even with partial magnetic shielding from Earth's field. A 2-year Mars mission might add 5%. That's already at the high end of what space agencies currently find acceptable for trained volunteers. For a 42-year interstellar mission in the open interstellar medium, these numbers extrapolate to radiation doses that would represent a significant portion of the crew's total cancer risk across their lifetimes. Radiation shielding helps. Water and polyethylene are effective at absorbing cosmic ray energy because of their hydrogen content. Hydrogen atoms efficiently slow secondary particles. Surrounding the crew's sleeping and living areas with meters of water or hydrogenous material reduces dose significantly. But every kilogram of shielding has to be accelerated to 10% of light speed and then decelerated. The fuel cost scales with the total mass of the ship. This is the inescapable trade-off. Better shielding means heavier ship, means more fuel, means even heavier ship, means even more fuel. Electromagnetic shielding, a magnetic field generated by superconducting coils around the ship, mimicking what Earth's magnetic field does for us, has been seriously studied as an alternative. It would deflect charged cosmic ray particles without adding significant mass to the shield itself. The power requirements are substantial, but manageable with a nuclear reactor. But electromagnetic shielding is useless against neutral particles. Some cosmic rays are neutral atoms. They follow straight-line trajectories, regardless of any magnetic field, and arrive at the crew compartment unimpeded. There's also a subtler complication. When cosmic rays hit shielding material, they can shatter atomic nuclei in the shield and produce secondary particle showers. Some materials are worse than others at this. Dense metal shields like aluminum can actually increase the dose inside by producing more secondary radiation than they absorb. Water and polyethylene are better, which is why they're preferred for spacecraft radiation shielding despite the mass penalty. The optimization problem of radiation shielding for an interstellar ship has no perfect solution with current knowledge. The honest assessment is that a crew on this journey would accumulate radiation doses representing a meaningful long-term health risk, even with the best feasible shielding. Not immediately incapacitating, not producing acute radiation sickness, but raising cancer rates and potentially contributing to other long-term effects. The question is whether the mission planners and the crew consider that acceptable. The crew, who volunteers knowing this information, is making a different kind of calculation than a soldier who faces combat. They're accepting a probabilistic, long-term risk in exchange for the certain experience of the journey and arrival. Whether that trade is worth it is a deeply personal decision. The people who make it will be a particular kind of human. Beyond cancer, there's an emerging concern about cosmic radiation and the brain. Galactic cosmic rays include high-energy, heavy nuclei, carbon, oxygen, silicon, iron, that are particularly damaging to neural tissue. Studies in rodents exposed to simulated galactic cosmic radiation show changes in neural structure, reductions in memory function, decreased problem-solving ability, and alterations in emotional regulation. The underlying mechanism involves damage to dendritic branching, the physical structure of neural connections, and to the chemistry of synaptic transmission. Whether these effects translate to humans exposed to actual space radiation at the doses expected on an interstellar journey is not yet fully established. But the animal data is concerning enough that NASA considers central nervous system effects of cosmic radiation one of its priority research areas for long-duration missions. For the crew of a ship to Proxima Centauri, this matters in a specific operational sense. they need to still be capable of complex judgment in year 40. The approach to Proxima Centauri, the decisions about whether and where to deploy probes, the management of whatever they find, all of this requires full cognitive function from people who have been accumulating cosmic radiation exposure for 4 decades. Any decline in cognitive capability is a mission risk. You can screen for radiation sensitivity. You can optimize shielding. You can monitor cognitive function throughout the mission. None of these eliminates the risk. They just manage it as well as possible. Let's talk about the interstellar medium itself. The space through which the ship travels is not a perfect vacuum. It contains gas, primarily hydrogen, the most abundant element in the universe, at densities of roughly 1 atom per cubic centimeter. It contains dust grains in smaller quantities. And it contains the galactic cosmic rays we've discussed. At the speeds relevant to everyday spacecraft, these are inconsequential. A grain of interstellar dust hitting a spacecraft at about 6 miles per second barely registers. At 10% of the speed of light, about 18,600 miles per second, the physics changes completely. Kinetic energy scales with the square of velocity. A dust grain hitting at 10% light speed carries roughly 10 million times more kinetic energy than the same grain hitting at 6 miles per second. A single dust grain, 1 micrometer in diameter, about the size of a bacterium, has a mass of roughly 1 to 2 picograms. At 10% light speed, that grain carries kinetic energy in the range of tens to hundreds of megajoules, comparable to a substantial explosive charge. From a bacterium-sized dust grain, a millimeter-sized pebble carries kinetic energy comparable to a small nuclear weapon. The interstellar medium doesn't have many particles large enough to cause catastrophic single-impact damage along any specific path. But over 42 years of continuous travel, the probability of encountering larger grains rises. And the cumulative effect of countless small impacts would erode any exposed material on the ship's forward face. The standard engineering solution is a dense erosion shield at the front of the ship. A thick block of material, perhaps a composite of layers, designed to absorb and distribute impact energy that takes the hits and ablates slowly over the course of the journey. The shield would be designed to still have material remaining at the end of the trip, but it would be significantly thinner at arrival than at launch. The specific design depends on how dense the interstellar medium is along the specific path, which is known from astronomical observations but only in average terms. Local variations exist. If the ship passes through a denser filament, the shield takes more damage than expected. The margins are built into the design, but margins are exactly that. Margins. Not guarantees. Gas atoms in the interstellar medium also contribute to erosion through a different mechanism. At 10% of the speed of light, individual hydrogen atoms hit the forward face of the ship with enough energy to knock atoms loose from the surface in a process called sputtering. The cumulative effect over decades is measurable erosion of any unprotected surface. Heat, generated by the constant particle flux, would need to be managed. The physics of the interstellar medium at these velocities is a genuine engineering challenge, not a background assumption. Now, let's address what special relativity actually does to this journey. At 10% of the speed of light, the Lorentz factor, the number by which relativistic effects scale, is about 1.005. This means that for every year that passes aboard the ship, about 1.005 years passes outside. The crew ages slightly more slowly than the universe around them. Over 42 years of ship time, the difference accumulates to about 77 days. The crew arrives about 77 days younger than they would have been had the same proper time passed at rest. This is real. It's been measured with atomic clocks in aircraft and satellites, and the numbers match the theory to extraordinary precision. But at 10% light speed, the effect is so small it barely matters for planning purposes. The journey takes 42 years. Accept it. The effect becomes genuinely significant at higher velocities. At 50% of the speed of light, the Lorentz factor is about 1.15. The crew ages at about 87% of the rate of outside observers. At 90% of light speed, the crew experiences a journey that takes about 4.7 years as measured outside, but only about 2 years in subjective ship time. That would make the journey genuinely feasible within a single working career. But reaching 90% of light speed with a crewed ship requires energy inputs that dwarf everything we've discussed. The relativistic mass increase as you approach light speed. The fact that each additional increment of velocity requires more and more energy per unit of gained speed makes the last few percent toward light speed almost impossibly expensive in energy terms. At 99% of light speed, the effective mass of the ship is about 7 times its rest mass. You're not just accelerating the ship. You're accelerating the energy you've already put into accelerating it. Light speed itself is not just fast. It's the boundary of what's physically possible for objects with mass. No amount of energy can push a massive object all the way to it. Time dilation is real and useful. But accessing it at the levels that genuinely compress 42 years to something a human crew can live through requires velocities that current physics places in a different league of engineering. Challenge from anything else we've discussed. At 10% light speed, plan for 42 years. Let's now construct the approach to Proxima Centauri. After years of deceleration, the engines burning in the direction of travel to slow the ship from its interstellar cruise velocity, Proxima begins to grow in the instruments. Not dramatically at first. Red dwarfs are dim. Even close up, Proxima's apparent brightness, as seen from a ship still light months away, is not impressive. But it's growing. Week by week, the disk resolves. The planet Proxima Centauri b becomes detectable as a separate body. Months out from orbital insertion, the crew begins systematic characterization of the system. Their telescopes and spectrometers have been studying Proxima from farther out, but now the resolution improves with proximity. Proxima Centauri b's orbit has been tracked from Earth for decades. Its position is known. The ship's instruments point at it and begin their work. The planet is rocky, as expected, larger than Earth, consistent with the minimum mass of 1.27 Earth masses, established from the radial velocity measurements back home. The surface resolves in increasing detail as the ship approaches. It doesn't look like Earth. It doesn't look like Mars either. The light from Proxima dim, red-orange, with a different spectral character than sunlight, illuminates a surface that reflects it in an unfamiliar way. The day side is visible as a continuous hemisphere under constant illumination. The night side is permanent darkness. The terminator, the boundary between the two, is sharp, a ring circling the planet where the star's light just grazes the surface. This is the confirmation the ship needed. Proxima Centauri b is tidally locked, one face permanently toward its star, the other permanently away. The day-side surface temperature is high, not as extreme as Venus, but with a thick carbon dioxide atmosphere, it could climb past 120 degrees Celsius, which is about 248 degrees Fahrenheit, far above what any complex life we know could tolerate. The night side is deeply cold, plunging well below freezing, potentially colder than minus 40 degrees Celsius, which is also about minus 40 degrees Fahrenheit. The point where the two scales happen to meet. In the terminator zone, the spectrometers find something more interesting: atmospheric gases. The planet has an atmosphere. Carbon dioxide dominates, with nitrogen as a substantial secondary component. Water vapor is present in trace amounts. There is no detectable free oxygen. No oxygen means no photosynthetic life, producing it in large quantities, which is significant. But the presence of water vapor means water is part of the chemistry of this world. Whether it exists as liquid anywhere on the surface is a harder question. The greenhouse effect of the carbon dioxide elevates temperatures above what Proxima's dim light alone would produce. In the terminator zone, where temperatures might be moderated between the extremes of day and night, liquid water could theoretically exist in some locations. The atmospheric circulation is also complex. Hot air rises on the day side, flows at high altitude toward the night side, cools and sinks, returns along the surface. The result is strong, persistent winds in the terminator zone, where the temperature gradient drives the circulation most intensely. Surface winds could be hurricane force, driven not by weather fronts, but by the fundamental geometry of the planet's illumination. The crew notes this as a landing challenge. It's not the first landing challenge they note. Proxima Centauri is not a calm star. Red dwarfs are small and cool, but they are not sedate. They produce stellar flares, sudden releases of magnetic energy that emit intense ultraviolet light, X-rays, and bursts of charged particles. Proxima is among the more active red dwarfs known. It has been observed producing superflares that release energy hundreds to thousands of times more than typical solar flares from our Sun, on timescales of days to weeks. A planet orbiting as close to Proxima as Proxima b does receives these flares at crushing intensity. Our Sun occasionally produces significant flares. Major events like the Carrington event of 1859, which disrupted telegraph systems globally and would cause catastrophic damage to modern electronics, infrastructure, occur roughly once per century. Proxima produces events of comparable relative magnitude on timescales of days. The surface of Proxima b is irradiated with intense ultraviolet and X-rays on a schedule that makes sustained surface chemistry very difficult to maintain. Whether any atmosphere persists at Proxima b depends critically on whether the planet has a magnetic field strong enough to deflect the charged particle component of Proxima's flares. A magnetic field strong enough to do this requires a convective, electrically conducting, rapidly rotating planetary core driving a dynamo. Smaller, rocky planets cool faster than larger ones. A tidally locked planet rotates slowly, one rotation per orbital period, in Proxima b's case, 11 days. Slow rotation is less favorable for a strong dynamo than fast rotation. The likelihood that Proxima b has a robust protective magnetic field is uncertain. If it doesn't, its atmosphere has been steadily eroded over billions of years by the stellar wind and flare-associated particle bombardment. The instruments are picking up both a current atmosphere and evidence that it has been significantly thinner in the past. The ancient terrain shows features consistent with a thicker atmospheric history. Erosional features. deposition structures, valleys that look like they were carved by flowing liquid. What this planet was like billions of years ago, under potentially different stellar activity and atmospheric conditions, is a different question from what it is today. What it was like then might have been very different. Maybe habitable by life. Maybe even inhabited by life. The thought is not presented as a certainty. It's presented as a question the crew has to take seriously and investigate responsibly. Planetary protection is the framework for thinking about what to do next. When Mars missions are planned, they include strict protocols for sterilizing spacecraft to prevent Earth organisms from contaminating Mars. The concern is that Earth life, if introduced to an environment where it could survive and spread, would confuse any future search for native Martian life. An interstellar mission faces this question with far higher stakes. Earth organisms are extraordinarily resilient. Bacterial spores can survive vacuum, intense radiation, and temperature extremes that would destroy almost anything else. They could survive a descent through Proxima B's atmosphere. They could potentially establish themselves in some protected niche. If Proxima B hosts any remnant biology, even microbial life in subsurface environments, in sheltered rock structures, in any pocket where conditions are less extreme than the surface, introducing Earth organisms would create a contamination problem that might be impossible to resolve. You would forever be unable to determine whether any biology found on the planet is native or introduced. The mission's central scientific question, does life exist elsewhere, would become unanswerable because you answered it too carelessly. This is why the sequence of investigation matters. Weeks and months of orbital observation first. Then, sterilized robotic surface probes, designed and built under conditions comparable to the most stringent spacecraft sterilization requirements ever imposed. Sample analysis in sealed containment aboard the ship. Slow, careful, responsible. If any sign of extant or past life is detected during the robotic phase, the protocols tighten further. Human descent to the surface, if it happens at all, comes only after extensive characterization and with full sterilization of the crew members and equipment. The crew would push against these restrictions. They've been traveling 42 years. They're standing in orbit above a planet that might have life. The desire to go down is overwhelming. But the mission planners built the protocols into the mission culture before launch for exactly this reason. The crew would follow them. Not easily, but they'd follow them. When the surface probes finally transmit results back to the ship, the picture is complicated. The terrain in the Terminator Zone shows ancient sedimentary structures. Rock layers that could only form in standing liquid. Dry beds of what were once bodies of water, enormous compared to anything in the current thin atmosphere. This planet had substantial liquid water on its surface at some point in its history. The geochemistry of some rock samples, analyzed by the probe's instruments, shows distributions of organic molecules that are statistically unusual, not clearly biological, but not easily explained by simple abiotic chemistry either. Complex carbon compounds in spatial distributions that, on Earth, would be associated with biological concentration. The crew's scientists argue about what it means. Some believe the signatures reflect ancient biology organisms that existed when the planet had a thicker atmosphere and more favorable surface conditions, whose chemistry was preserved in the rock over billions of years of subsequent harsh conditions. Others believe the signatures are explicable through photochemistry. The action of Proxima's radiation on carbon-containing gases in the ancient atmosphere, producing complex organics that accumulated in liquid water bodies and concentrated when the water evaporated. Both explanations are physically plausible. The instruments aboard the ship are not decisive. To answer the question definitively would require getting below the surface, where any remnant chemistry or biology would be best preserved, and where the analytical tools needed would require either a more capable robotic mission or a human presence with proper containment. The crew has the tools for the latter. They have human scientists who could do the work. They have the capability, given what they've brought aboard, to set up a contained laboratory for analyzing subsurface samples with techniques sophisticated enough to distinguish abiotic chemistry from biology. What they don't have is certainty that doing so won't inadvertently introduce Earth contamination. The debate is genuine. There are no clean answers. And the messages they send back to Earth, asking for guidance, take 4.24 years to arrive. The responses won't come back for another 4.24 years. 8.5 years for a round-trip conversation. This decision is the crew's to make. They make it carefully. They make it together. And they take months to reach it. Let's step back from the planet itself and think about the broader experience of what it means to have arrived here. The crew has traveled 42 years. They've aged. Some of them, statistically, will have faced serious health challenges during the journey. The people who stand in this ship's habitat ring, looking at Proxima Centauri through the observation windows as a visible disk of reddish light for the first time, are not the same people who boarded the ship on Earth. Not just because they're older, because 42 years of the journey has happened to them. They've built their deepest relationships aboard this ship. Whatever connections existed back on Earth are now connections with people who are themselves 42 years older, who have sent messages that arrived years after they were sent, whose lives the crew has watched in asynchronous fragments across decades. If crew members had parents alive when the ship launched, those parents are most likely no longer alive. Friends from before the mission have lived their entire adult lives, had families, changed in ways that the crew has observed only through the narrow band of delayed communication. Earth is still there. The crew knows this. They receive regular updates. But Earth has become something they relate to the way a person might relate to the country their grandparents emigrated from. Known, connected to, but not home in any lived sense. Proxima Centauri is not home either. Not yet. Not in the sense of familiarity or belonging. The crew exists between things. Past one star, arrived at another, citizens of the transit. This is genuinely novel territory for human psychology. No human being has ever held this particular relationship to their origin and their destination simultaneously. The emotional reality of it is something that could be prepared for, studied, modeled, anticipated, but not fully understood until you're in it. The communication situation has evolved over the journey in ways worth describing. At launch, messages take light minutes to cross to Earth. Normal conversation is possible, albeit with delays. By the time the ship is a light week from Earth, the rhythm of communication has shifted. You send a message and wait. Days pass before the response arrives. By a light month out, the exchange is something more like letters than conversation. A light year out, you're exchanging messages that arrive a year apart, containing a year's worth of life changes and developments, compressed into whatever the sender thought worth transmitting. The crew learns to write differently. They learn to compose messages that acknowledge the delay, that address what the recipient might have experienced since the previous exchange, that exist as time capsules rather than real-time communication. The people back on Earth learn to read them differently. A message from someone on the ship describes what was happening aboard a year ago. The person who sent it is a year older now. The ship is a year farther along. By the halfway point of the journey, messages exchanged between Earth and the ship are separated by over 20 years in round-trip time. The exchange continues. But it's a different kind of relationship than any existing framework in human experience. The crew would be closest to each other. The people on Earth closest to each other. The connection between the two groups would be maintained through this slow, asynchronous communication, a thread stretched to extraordinary length, but not broken. Until eventually, if the mission settles at Proxima and no return is planned, the thread becomes the permanent form of contact between two branches of humanity. Messages continuing for as long as anyone bothers to send them. Humanity talking to itself across 4 light years. Now, let's consider the return trip question directly. For a crew that departed at 30, a return trip from Proxima to Earth would require another 42 years of travel. They'd arrive on Earth at around 114 years old. That's beyond the current human lifespan. Even with the medical advances of a civilization capable of building an interstellar ship, the return trip for a crew that makes a simple out-and-back journey is either impossible or requires radical life extension medicine that we can't assume will exist. The realistic design for a crewed mission to Proxima Centauri is a one-way mission. Not one way in the sense of a suicide mission. One way in the sense that the crew permanently relocates to the Proxima system. They build whatever presence is possible at the destination. They explore. They establish a station. They live out the remainder of their lives doing the work they came to do and sending everything they discover back to Earth. The people who make this decision understand it fully before they board the ship. They know there is no return ticket. They've accepted this. But accepting it before departure and living it over 42 years of increasingly deep commitment to the decision are two different experiences. At some point during the journey, the weight of permanence settles in a way that understanding it never did. The crew carries that weight. They do so in different ways, at different times, with different levels of ease. The mission succeeds or fails, partly on whether they can carry it together. What about a small number of possibilities that sometimes appear in discussions of interstellar travel and deserve brief, honest engagement? Suspended animation, some form of induced hibernation that dramatically slows biological processes. So the crew sleeps through most of the journey and arrives physiologically younger than they would if they were awake for 42 years. This is biologically possible in principle. Many animals hibernate. Some undergo processes that are more extreme tardigrades can survive near-complete metabolic shutdown under extreme conditions. For humans, true suspended animation at the level needed for decades of preservation while still being fully revivable is not a technology that currently exists. We've achieved cooling-induced reduction of metabolic rate in medical contexts, mostly for short surgical procedures. We have not achieved anything close to decades-long human suspension with intact personality, memory, and health upon revival. Whether it's achievable is an open question. but it's an open question that requires solving very difficult biology, not just improving current techniques. The idea of hibernating crews for 42 years and waking them at arrival is appealing. It avoids the psychological problems. It avoids some of the biological aging concerns. It completely changes the character of the mission, but it can't be assumed. Embryo missions are another concept sometimes discussed. Send frozen human embryos rather than adult crew, with automated caretaking systems that can raise children at the destination. The ethical problems with this approach are severe and probably disqualifying. Raising humans without parents or community in an automated system, purely as instruments of a mission decided before they existed, doesn't meet any ethical standard for treating people as ends in themselves rather than means. These are worth mentioning, not to dismiss them, but to be honest that they come with their own requirements or their own deep problems. The mission arrives. The work is done as well as it can be done. The crew has spent years in orbit, deployed probes, analyzed samples, mapped the planet's terrain in detail, characterized Proxima's activity, monitored the atmosphere, compiled a scientific picture of this system that Earth's astronomers would take decades to fully digest. The messages carrying this data take 4 years to reach Earth. When they arrive to a planet where the people who launched the ship are now 46 years older. The scientists who planned the mission are mostly retired, some of them gone. A new generation of researchers receives the data and begins the work of interpretation. In some sense, the mission talks to a different Earth than the one that launched it. The continuity is institutional, not personal. The agencies and universities that planned the mission have continued. The people have changed. The questions have evolved. Some things the crew discovers will answer questions that seemed important in the year of launch, but have since been superseded by other discoveries made back in the solar system. Some things will be genuinely new, answering questions that hadn't even been asked when the ship departed. The data from Proxima Centauri will be the most significant scientific return in human history. No instrument ever launched from Earth could observe what the crew of this ship has observed from inside the Proxima system. The organic chemical signatures on Proxima B's surface, the characterization of Proxima's flares in real time from close range, the detailed atmospheric chemistry, the ancient lake beds and their preserved chemistry. Whatever answer the crew's careful investigation produces about the presence or absence of life, past or present, all of it arrives on Earth 4 years after it was sent, and then takes another 4 years to get a response, if anyone has a response worth sending. This is the journey. Not glamorous, not cinematic, but real in a way that the cinematic version never is. It's 42 years of a ship full of aging people living their lives in a metal environment, doing science, managing conflict, grieving losses, celebrating small events, maintaining their equipment, watching each other grow old, and periodically sending messages to a home they'll never see again. It's radiation accumulating slowly in their cells. It's dust erosion carving slowly into the ship's forward face. It's the governance structure adapting as the original crew members age and the dynamics of leadership shift. It's what the ship's garden looks like after 20 years, when the hydroponic systems have been modified 8 times by successive generations of maintenance. It's the first time someone is seriously ill, and the medical team does everything they can. It's the first time the instruments fail in a way the backup system can't fix, and the engineering team improvises a solution that no one on Earth would have thought of. Because no one on Earth has the specific knowledge these people have accumulated. It's 42 years of being the only humans in the universe who know what interstellar space feels like from inside it. And then it's arriving. Proxima Centauri, ahead of you, visible as a disk. Proxima b, below you. The data streaming in. The crew that's done something no human has ever done. The beginning of whatever comes next. There is another category of challenge that deserves its own careful consideration. Navigation. It sounds straightforward. You point the ship at a star and fly toward it. The reality is considerably harder. Stars are not stationary. Every star in the Milky Way is moving, orbiting the galactic center at its own velocity on its own trajectory. Proxima Centauri is moving relative to the Sun. When you look at Proxima, you're seeing where it was 4.24 years ago, because that's how long the light took to reach you. When you launch a ship, you're not aiming at where Proxima is. You're aiming at where it will be when the ship arrives, 42 years from now. 42 years of Proxima's motion needs to be calculated and built into the trajectory. This is feasible. Proxima's motion has been measured accurately enough to project its position decades into the future. But there's more. The ship itself is moving through a galaxy full of masses. The gravitational influence of every star the ship passes near, every dense region of the interstellar medium, every rogue planet or dark body drifting through the void, all of them exert tiny but real gravitational tugs on the ship's trajectory. Most of these are negligible. Some are not. A close pass to an unseen object, a rogue planet, or a very faint brown dwarf could introduce a trajectory deviation that, over the remaining years of the journey, compounds into a significant miss. The ship needs to continually measure its actual position against its predicted position and make corrections. These corrections are small burns of the engine, course adjustments. Each one uses fuel. Fuel that has to be budgeted carefully against the 42-year journey and the deceleration requirement at the end. Navigation also becomes relativistically complex at 10% of light speed. At this velocity, the positions and apparent brightness of stars shift measurably due to relativistic effects. Stars ahead of the ship are slightly blue-shifted and appear slightly brighter than they do from Earth. Stars behind are red-shifted and appear dimmer. The whole stellar background is subtly warped from what any Earth-based star chart describes. The navigation software has to account for this, because the stars the crew uses to triangulate their position don't look quite like the stars in the catalogue they brought with them. This is manageable with modern computational tools. But it adds complexity. And it means that the navigation systems need to have relativistic correction built in from the start. Something that has never actually been needed for any spacecraft in human history, because none has ever traveled fast enough to require it. The ship also needs to maintain its orientation precisely. The habitat ring is spinning. The main body of the ship may or may not be spinning. Gyroscopes maintain orientation. Gyroscopes drift over time. Star trackers, sensors that identify known stars and compare their positions to a catalogue to determine orientation correct for gyroscope drift. Over 42 years. The maintenance of precision orientation requires that the star trackers and gyroscopes remain functional. Backup systems exist for when they fail. Backup systems for the backup systems. calibration procedures done regularly throughout the mission. This is routine engineering, but it's engineering that has to work without fail for 4 decades. There's a question that nobody asks in discussions about journeys to Proxima Centauri that probably should be asked. What do you do for 42 years? Not, what does the ship do? What do the people do? The mission has scientific objectives. The crew collects data about the interstellar medium throughout the journey. This has genuine value we've never had sustained in situ measurements in the interstellar medium from a crewed vessel, and the data would be extraordinary. But this science doesn't require the sustained attention of the full crew for all of 4 decades. The ship runs largely automatically. Systems operate continuously under computer control. The crew monitors, maintains, and intervenes when needed. But you can't monitor monitors every waking hour for 42 years. The people need to live. Some crew members would be doing science throughout, analyzing interstellar medium data, building up long baseline observations of stellar positions from the ship's unique vantage point, studying the sun from an unprecedented distance and angle. There's no shortage of legitimate scientific work, but not for everyone. All the time, for 42 years. The ship would need to function as a society, not just a crew. People would develop interests, skills, and occupations that go beyond their formal mission roles. The ship might have a library, not a database. A real library. A physical or virtual collection of accumulated human knowledge, literature, music, art, film, games, sports, everything that helps a community remember what civilization feels like. Some crew members would spend years reading. Others would spend years making things, building equipment that no mission planner anticipated, cooking elaborate meals from the hydroponic harvest, writing fiction about worlds they've never seen. A few would become the ship's historians, documenting what daily life is like aboard an interstellar vessel, not for science, but because someone should record what this is. Relationships would deepen in ways that only decades of shared experience can produce. Friendships would form that are unlike any on Earth because they exist in this specific context of isolation and shared purpose. Romances would develop. The ship's social policies on relationships would need to be established before launch and refined in practice. On such a small vessel, relationship dynamics affect the social fabric in ways that larger communities absorb without noticing. A conflict between 2 crew members in the 5th year of the journey affects the group in ways that a conflict between 2 office colleagues does not. The ship's governance structure would need to handle this. Culture would evolve. The ship's culture at launch would be Earth's culture of that era, carried by the crew who grew up in it. By year 20, that culture has already changed. References to Earth, events that happened after departure, arrive in messages, contextless, referring to things and people the crew doesn't know. The crew begins developing references of their own, in-jokes that only work aboard the ship, traditions that emerged from specific events during the journey, language that's drifted slightly from Earth's, picking up idioms that make sense in this environment. A year on the ship means something different from a year on Earth, even when the ship uses the same calendar. A year on the ship is defined by arbitrary convention because there's no sun rising and setting, no seasons, no natural cycle to anchor it. The crew creates their own cycles, holidays, anniversaries. regular gatherings that mark time and reinforce community. All of this is the work of 42 years. The science is part of it, but only part. Let me describe something specific about what the first human to look out a window and see Proxima Centauri, visibly larger than it's ever appeared in the history of human observation, would actually experience. You've been in this ship for years, decades. The star has been there in the instruments since launch. A point of light, growing slowly brighter as the years pass. The crew has tracked it so closely that they know its flare patterns, its rotation period derived from light variations, its spectral fingerprint. But until now, it's been a measurement, a number on a display, a feature in a spectrograph. And then one day, the instruments show something different. Not just a bright point, a disk. Small. Smaller than you'd expect, even knowing the distance. Red dwarfs are small stars, and even a few light months away they resolve as just a tiny disk. But a disk. Something with extent. Something your eye can recognize as an object rather than a point. The crew gathers at the observation windows. Proxima Centauri hangs there in the dark. A small, dim, deep red-orange sun. Nothing like the sun these people grew up under. Dimmer, cooler in color. More orange-red than yellow-white. The light it casts through the observation ports has a different character. Not the warm yellow of a summer afternoon. Something redder, dimmer, richer in the orange end of the spectrum. It's not beautiful in any conventional way that anyone would describe on Earth. But it's there. It's real. And it's the first time in the history of life on Earth that any living creature has looked at another star from close enough to see it as a disk with the naked eye. Whatever else happens on this mission, this moment is already something. Below the star, a tiny point that the instruments confirm is Proxima Centauri, b. Not resolvable with the naked eye from this distance. But the instruments show its disk clearly. A world. Another world around another star. 42 years to get here. And now the work begins. The actual science of the arrival phase would occupy the crew for years, maybe decades, depending on how long the mission's operational life extends. The characterization of Proxima Centauri's behavior from close range would be transformative for stellar physics. From Earth, Proxima's flares are detected and measured. From orbit around Proxima b, a crew could observe them as they develop. The magnetic structures on the star's surface that trigger flares. The propagation of the flare's energy outward. The interaction of the charged particle burst with Proxima b's atmosphere. All of this observed in real time, with instruments that are physically present in the system rather than looking at light that traveled 4 light years. The difference between studying Proxima from Earth and studying it from within its system is comparable to the difference between studying human metabolism from descriptions and actually being inside a cell. The resolution, the time cadence, the ability to observe spatial relationships, all of it transforms. Proxima Centauri b's geology, accessed through surface probes, would answer questions about planetary formation around red dwarfs that currently have no answers. How does tidal locking affect a planet's interior evolution? How does sustained high-energy radiation from an active star shape the chemistry of a rocky world's surface? What happens to carbon and nitrogen chemistry over billions of years on a world bombarded by ultraviolet light with an evolving atmosphere? The answers would take years to compile, even from a position in the system. The crew would be busy. Genuinely, scientifically, productively busy. Not in the way of filling time. In the way of doing work that matters, and that could only be done here, in this system, with these instruments, from this vantage point. That would sustain them. Purpose sustains. Meaning sustains. The mission has both in abundance at this phase. Then there's the question of what they leave behind when their operational capability begins to decline. Not from failure, but from age. The crew has been traveling since their 30s. They're in their 70s at arrival. After a decade of work in the Proxima system, they're in their 80s. A small crew in their 80s, operating a ship that has been in service for over 50 years in a stellar system where no help is available. The mission profile has to include a transition. Not an ending, but a change in the nature of what the mission is. Automated systems take over more and more of the ship's functions as the crew's capacity to actively manage things declines. Scientific instruments that can operate autonomously, collecting data and transmitting it to Earth without requiring constant human management. Systems designed to continue functioning after the crew is no longer there to oversee them. A legacy infrastructure. The crew, throughout the operational years, would be working on building this. Not just doing science, building the scientific infrastructure that continues doing science after them. Calibrating automated instruments. Writing the software that directs what to observe and when. Setting up long baseline experiments that will run for years after the crew's time is done. Creating records, detailed, comprehensive records of everything observed, everything learned, everything tried. So that Earth, receiving it 4 years after it's sent, can continue building on the work. The mission doesn't end when the crew's working years end. The mission continues as long as the automated systems function. Maybe decades more, maybe longer, if the systems were built robustly. The crew's last contribution would be ensuring the continuity of the mission they carried across 42 years of space. It's a particular kind of work, building something that will outlast you. Not unusual in human history. People have always built things for futures they wouldn't see. Cathedrals, libraries, infrastructure, scientific observatories that would take a century to pay their full scientific dividend. The interstellar mission is this in its most extreme form. Every person who boards the ship knows they are building something for a future that begins before they're done, but that extends far past them. That's the character of the work. And the kind of people who choose it are the kind who find that motivating rather than discouraging. There are questions that will never be fully answered by this mission, even with everything the crew does. The most profound one is the one that motivated the mission most deeply. Whether life exists or ever existed. At Proxima Centauri b, the crew will have better data than anyone. They will have analyzed the surface chemistry with instruments no telescope on Earth could replicate. They will have drilled into the ancient lake beds and analyzed what's preserved there. They will have looked for the specific molecular signatures that distinguish biology from chemistry, and they will have done this carefully, over years, with the full analytical capability the mission carried. And they still might not have a definitive answer. Because the question of whether life exists or once existed somewhere is not always a question that yields to data alone. Sometimes the data is ambiguous. Sometimes the chemistry is consistent with life, but also consistent with complicated abiotic processes. Sometimes the preservation is insufficient for any existing analytical technique to distinguish between the two. This is not a failure. It's the nature of the question. Astrobiology, even practiced at the source, may not always give you a yes or no. It may give you a probability, a well-informed probability, grounded in decades of careful observation, but not certainty. If the crew concludes, "We found evidence consistent with past biology, but cannot confirm it definitively," that conclusion will be both the most scientifically honest answer possible and one of the most frustrating things humanity has ever heard. Because we want to know. The desire to know whether we are alone, whether life is a singular accident of Earth or a feature of the universe, is one of the deepest drives in human intellectual history. And the closest star might provide only a maybe. The crew would understand this. Scientists always understand this better than anyone else, because scientists live with ambiguous results their entire careers. But they would also know that their maybe is better grounded than any guess made from Earth, that it represents decades of careful work at the source, that future missions, with better technology, could build on what they established, that the work doesn't stop just because the first answer isn't clean. Science rarely gives clean first answers. It gives better and better approximations of the truth. And this would be a genuinely better approximation than anything we've had before. When you look up tonight and think about Proxima Centauri, 4.24 light-years away, a dim red point that requires a telescope to see you're looking at a star that's been burning for nearly 5 billion years, older than the Sun. It will still be burning in another 4 trillion years, long after the Sun has ended and the inner solar system has been consumed. There's a planet orbiting it every 11 days. There's ancient geology suggesting past liquid water. There's chemistry we haven't fully explained. There's the possibility, not confirmed, not ruled out, of life that once existed there before the conditions turned hostile. All of that is sitting out there, 25 trillion miles away, and we currently have no way to reach it with any speed that would matter in a human lifetime. There's one more dimension to this journey that doesn't fit neatly into propulsion physics or radiation biology or planetary protection protocols. What it means for humanity as a species. Not in an abstract philosophical way, in a concrete, structural way. Right now, all of humanity exists on one world. We have people in orbit above it. We have probes throughout the solar system. But every living human being is on Earth, dependent on Earth, tied to the fate of Earth. If something catastrophic happened to Earth, an impact, a supervolcano event, a pandemic, unlike anything in recorded history, a climate shift beyond recovery, humanity ends. Not some of humanity. All of it. The entire accumulated project of 4 billion years of evolution on this planet, producing in its final moments a species capable of understanding its own origin and building machines that can leave the gravity well, ends because everything was on one rock. A crewed mission to Proxima Centauri doesn't fix this immediately. A small crew in a distant star system is not a meaningful backup for all of humanity. But it begins a process. It establishes the principle that humans can exist somewhere other than Earth. It creates the first permanent human presence outside the solar system. And if that presence can sustain itself, if the infrastructure built in the Proxima system can eventually support more people, more capabilities, more long-term habitability. Then the calculation begins to change. Over centuries, over generations. The human story could spread to other stars the same way it spread across Earth. Slowly and at enormous cost and with many failures, but eventually establishing a kind of presence that no single catastrophe can eliminate. This is one of the deepest arguments for making the journey. Not the science, though the science is extraordinary. Not the exploration, though the exploration is historic. But the basic calculus of not having everything in one place. The crew who takes this journey knows this. It's part of why they go. Not the whole reason, but part. There's also the question of what it means to the people left on Earth. Humans are meaning-seeking creatures. We construct narratives about who we are and what we're doing. A species that has sent people to another star is a different kind of species than one that hasn't. Not genetically. Not in any measurable biological way, but in how it understands itself. In the stories it tells about what's possible. In the horizon that children who grow up after the launch look toward. The Apollo missions did this for a generation. The knowledge that humans had walked on the moon changed how people thought about what was achievable. Not because it directly improved anyone's daily life, because it moved the horizon. A mission to Proxima Centauri would move the horizon in a way that the moon landing, extraordinary as it was, couldn't approach. It would say, the stars are reachable. Not easily, not quickly, not cheaply, but reachable. And a species that knows the stars are reachable is a different species than one for whom the stars remain permanent, unreachable lights. That change in self-understanding has consequences that no one can fully predict. But the horizon moved. And once a horizon moves, it can't be moved back. The stars become, for the first time in human history, part of the world where people actually go. Not the mythological world. Not the abstract world of equations and catalogues. The real world. The world of lived experience. That changes what it means to be human in ways we haven't had to think about yet. But we will. There's one category of outcome that deserves specific acknowledgement, because it's the one people are most reluctant to consider. The crew arrives. The instruments run. The probes descend. The samples are analyzed. And the answer comes back, nothing. No past life. No chemistry that requires biology to explain. A world that had liquid water billions of years ago and produced only abiotic chemistry. A planet that formed in a habitable zone around an active red dwarf and never got life started before the conditions deteriorated. A dead world that was never anything but dead. This is a scientifically important result. It tells us something essential about how common life is. But it's not the discovery anyone hoped for, and the crew has to sit with that. They've traveled 42 years. They've given everything the mission required. They've built a scientific legacy that will take Earth decades to fully digest. And the headline answer, the one that mattered most to everyone who watched the launch, is no. Or at least, not here. Not at the closest star. The emotional weight of that moment would be real. It would be processed differently by different crew members. Some would find meaning in the rigor of the investigation itself. Others would feel a specific kind of grief that doesn't have a name yet. The scientific community on Earth would absorb the result and update their models of planetary habitability around red dwarfs. The public would feel something harder to categorize. But here's what the result doesn't change. It doesn't change the fact that the journey happened, that humans were there, that another stellar system was visited, observed, and characterized at a level of detail no instrument on Earth could achieve, that the next mission can build on what was established, that the negative result at Proxima says nothing about what's at Barnard's star, or Wolf 359, or Epsilon Eridani, or any of the hundreds of other nearby stars with planets that we've already detected. A negative result at the closest star doesn't close the search. It refines it. The universe doesn't owe us a confirmation at the first site we visit. It just sits there, full of possibilities we haven't checked yet. That's what the crew would know. That's what they'd send back to Earth in their final reports. Not a triumphant declaration, but not a failure either. Just the truth of what they found, delivered honestly from the only people who had ever been there. And on Earth, 4 years after the messages arrived, someone would already be working on the next ship. It's worth stating plainly that no one alive today will see a ship launch toward Proxima Centauri. The development time required is too long. The engineering gap is too large. This is not pessimism. It's realism applied to a timeline problem. The people who will board that ship are not born yet. The people who will design its propulsion system are probably not born yet. The people doing the early theoretical work that eventually makes the engine possible are doing that work right now, in universities and research labs, and many of them will never know that their work was the foundation. This is the nature of large civilizational projects. They outlive the people who start them. The builders of the first cathedrals never saw them complete. The scientists who established the theoretical basis for nuclear physics didn't know what it would eventually enable. The engineers who built the early computing systems that led to the modern internet couldn't have described what they were actually building toward. Progress is built by people who can see the next step clearly, even when the destination is far beyond their horizon. The people working on fusion propulsion today. The people studying cosmic radiation biology. The people designing closed ecological life support systems. The people studying the psychology of extreme long-duration isolation. All of them are doing the next step. All of them are building towards something that none of them will see completed. That's how the journey to Proxima Centauri gets built. One step at a time. By people who care enough about the destination to work on it, even though they'll never arrive. When you look up tonight and try to find Proxima Centauri, it's in the southern sky, below the naked eye visibility threshold. So you'll need a telescope. You're looking at a star that's been burning for nearly 5 billion years. A little older than the Sun, which has been burning for about 4.5 billion years. It will still be burning in another 4 trillion years, long after the Sun has exhausted its hydrogen, expanded into a red giant, and transformed the inner solar system beyond recognition. Red dwarfs are the slow, patient, extraordinarily long-lived workers of the stellar world. Proxima will outlast almost every other star visible to the naked eye tonight. It burns cool and dim, and it lasts. There's a planet orbiting it every 11 days. There's ancient geology on that planet suggesting liquid water once shaped its surface into shapes we recognize: riverbeds, lake basins, sedimentary structures. There's chemistry in the ancient rock that hasn't been cleanly explained. There's the possibility, not confirmed, not dismissed, that conditions favorable to life once existed there. before something changed. All of that is sitting out there, 25 trillion miles away, around a star so dim you need optical assistance to find it in a dark sky. Humanity has known Proxima Centauri existed since 1915. We confirmed a planet around it in 2016. We've been thinking about visiting it seriously since at least the 1970s. Every year, the physics of the journey is better characterized. Every year, the specific engineering problems are a little more defined. Every year, the gap between understanding what it would take and being able to do it closes slightly. We are not close to launching. We are closer to understanding what would need to be launched. And the distance between understanding the requirements and meeting the requirements has been closed before, for problems that look just as impossible from the outside. The characterization of the challenge is done. That's different from the challenge being solved, but it's the essential first step. You can't engineer a solution to a problem you haven't fully specified. The specification is built. The propulsion gap has specific dimensions that specific research programs are working on. The radiation challenge has specific physics that specific shielding approaches are targeting. The life support duration problem has specific biological requirements that specific research programs are addressing. The psychology of long-duration isolation has specific identified risk factors that specific training and mission design concepts are trying to mitigate. None of these research programs will deliver a working interstellar ship on any near-term schedule. But they're moving. They're building the foundation that a working ship eventually stands on. The people who will design the actual ship haven't been born yet. They'll inherit this work. They'll inherit the knowledge that fusion propulsion is where the energy density needs to come from, that hydrogen-rich materials are where the radiation solution lies, that rotating habitats are where the bone density answer is. They'll start at a point that today's researchers spent careers building to, and they'll build further. That's how every large technological project in human history has actually worked. Not one generation solving everything. Each generation solving some of it and handing the rest forward. The journey to Proxima Centauri will be built across many generations of work before anyone boards a ship. The people who eventually board it will be the beneficiaries of generations of effort by people who will never know if it worked. That's a particular kind of faith in the work. The same faith that drove everyone who planted forests they'd never see mature, built institutions they'd never see realize their full purpose, laid the intellectual groundwork for discoveries that happened long after them. It's the most persistent thing in the human story. The closest star to us is 4.2, 4 light-years away. It has planets. One of them sits in the zone where liquid water is at least theoretically possible. There's ancient evidence of liquid water on its surface. There's chemistry that needs explaining. And someday, if we remain what we have always been, a species that goes, regardless of what it costs, regardless of how long it takes, someone is going to go there. The star is waiting. It has been waiting for nearly 5 billion years. It will wait. Good night.